Good morning, everybody. Happy Wednesday. Well, 2.5 weeks left here. I don't know if any of you are intrigued by quantum mechanics or quantum physics. Usually there's a small number of people that decide to become physics majors because they think that those ideas are cool and they want to study them. That was kind of part of what attracted me to physics. But as people are actually trying to do practical things with quantum mechanics, like make quantum computers, one of the puzzles they have to solve is this problem of entanglement. Has anybody ever heard that term before? It's one of those weird things in quantum mechanics where basically object one can influence object two, even though there is not enough time by the rules of classical physics for information to pass between the two of them. And in fact, that's one of the reasons why some folks are interested in quantum computing, is they think they will be much more secure than our existing methods of computing. So these are folks at the University of Copenhagen. I don't understand almost anything about the specifics of their experiment, but they have actually now shown quantum entanglement between two different systems, one of which is actually a mechanical oscillator. So there's the little sliver of connection to this semester, because our last unit we're going to get to here in a couple of weeks is about oscillations and motion that is periodic. I don't know exactly what system they were using that was a mechanical oscillator, but they were able to entangle that with a spin oscillator. So if any of you have studied any chemistry, you might know that the model is, there's an electron orbiting a nucleus, right? So if they orbit or precess in a given direction, that actually produces a tiny little magnet, basically, in that atom, and that sometimes gets referred to as the spin of the atom as well. So, yeah, I don't know, I thought that was kind of interesting. If you are a physics major, you get your first crack at quantum mechanics in the modern physics course, which comes up in the spring semester of the second year typically. And then if you like this stuff, you can take quantum mechanics through the full course on quantum mechanics typically as a junior or senior. So let's see, we've got assignment 30 due tonight. 31 is available, but it says due Wednesday. It's not due Wednesday, due Monday. It is not due on Friday because Friday is our exam. This afternoon is the last colloquium where there are undergraduate research presentations, so if you want to join us at 4, it's the same link we're using all semester long, but I'll try to remember to resend that out if that's helpful. And you have a Unit 10 summary due tonight as well. Most pressing on our agenda, obviously, is the exam that's happening on Friday right here. So it has 5 problems on that exam. One of them is a laboratory-based question, and so you should be prepared for that. Basically, you should be familiar with the things you've done in the laboratory here. So using the equipment you use, using the software we use, doing things like video analysis, producing a spreadsheet, analyzing a spreadsheet, all that kind of stuff is considered fair game when it comes to these lab questions. You can use the unit summary sheets that you've prepared if you've been doing those and turning those in. You can edit and tweak and add things to them after they've been graded if you wish to do so. But otherwise, the exam is closed book and closed internet. And again, we put this list up on Monday, but this is sort of my view of what the topics are that we've covered in units 6 through 10 there. So we, in unit 6, looked at free fall and projectile motion. 7 had a whole bunch of force topics, right? We did centripetal force, friction, tension, the normal force, how to sketch a free body diagram. 8 and 9 were the momentum units. So we introduced the definition of momentum, connected momentum, and specifically the change in momentum to impulse, how much force you apply over a time. And so that's the impulse momentum theorem. We did momentum conservation in 1 and 2 dimensions, introduced ways to find the center of mass, and then in unit 10, defined work, connected work to kinetic energy through the work energy theorem. And that was about it in terms of big topics there. So again, here in Unit 11, we're doing more energy stuff. It's not explicitly addressed on the exam too, but it doesn't hurt because it's energy ideas which build off of what we did here in Unit 10. So, any questions about the exam on Friday? Yes, it's fun. People love it. Again, if you've forgotten, but there is a previous exams folder up on Blackboard, so if you want to look at the last couple of years of tests and see what kinds of questions people got asked, you have the option to do so. So I think we got a fairly easy day agenda-wise today for where people are in getting done. So we've already defined gravitational potential energy, and I think most of you are in the midst of the section where you're dealing with conservative and non-conservative forces. My read on Unit 11 is that they give you the one new piece of information pretty early on there. Here's this thing called gravitational potential energy. Here's how you calculate it. Often mechanical energy is conserved, but now let's give you a bunch of scenarios for you to consider. Is this a reasonable situation to apply conservation of mechanical energy to? And sometimes the answer is yes, sometimes it's no. If the answer is yes, it often makes solving problems a lot easier in that domain. But in times the answer is no, and we have to use other techniques to do that analysis. So, the end ends with poppers. They have what I consider a kind of an odd equipment list there, because they say things you may need. Well, popper, yes. Platform scale, a 10 kilogram platform scale. I guess I get how you might use that, but they're talking about measuring or figuring out a number that represents the work needed to cock the popper, right, to invert it and get it ready to fly up. So if I take one of these little poppers, there's a certain amount of effort, that I have to exert on here in order to flip this thing around and get it ready to then set on my surface and pop up. So the whole goal here is to get an estimate of a number, and I guess this is not a 10 kilogram platform scale, it's a much more heavy duty platform scale, but I guess they're thinking you would push it down, but then you don't even get it inverted. So what we've always done in here is try to measure the amount of force you have to apply to invert it. And so there's the higher tech way you can do this. You can pull out your force probe and press in on it with your force probe over some distance, right? And that'll measure the force. And if you want to get really fancy with it, pull out your motion detector too. And then if your motion detector is pinging off the back of your force probe, like you hold the force probe here and you push it in, you'll actually collect data for both force and distance. And you can make a graph of force versus distance. And then just hit the integral feature there in Logger Pro and find the area under the curve. That's the work. If you want to do the lower tech version of that, you can invert the popper using a spring scale and just assume that whatever, find the average force of that interval and then pull out a meter stick or a ruler or something and estimate how much distance you have to move this thing through to cock it as well. Average force times distance again gives you a reasonable work number for that. So, I don't know, I would ignore the note about the platform scale there and be inventive when it comes to a way to find the work of that thing. Again, if you prefer, you can do the experiment with these. These fly higher in the air, they're more interesting. You'll just have to adjust because you can have this sit on the desk all day. It won't go anywhere. You have to sort of let it fall and hit the desk and then it goes up again. I'm not going to try it because Monday would took me, 7 tries to get it to actually go or something like that. Why I'm not an experimentalist, part 3. You can use those if you want, but you'll have to adjust your calculation to account for, hey, we're starting with some gravitational potential energy, right? And then as it falls, it gets transformed into kinetic energy, and then you release that stored elastic potential energy to produce the final height of that pop. So, all right, hopefully enough details on that, so you can go ahead and get started. It's like most people made it in today, but not everybody. Somewhat difficult. I'm gonna guess Achilles is gonna be here, because he's always here, he just comes in here.
Give him 10 minutes.
10 minutes.
Maybe 15.
So, John, before you get going, do you have Hopper data in your book from before, or are you guys gonna want to recreate that experiment at the end?
Yeah.
Okay, so when you get there, if you realize something's missing, let me know and we can recreate it over this computer. Okay, yeah, don't jump there if you're not there yet, but yeah, I'm gonna turn the laptop around too, so if you guys run into a question, hopefully I'll be able to see that when it's not turned around.